On page 1 of Rudin's Principles of Mathematical Analysis, we have a claim. So he claims that there is no rational number p such that p squared equals 2. And I haven't read this book for several years, and in particular I don't remember how this proof goes, so we're going to try to figure it out together. Now this is what's interesting about this claim is that if this is true, so let's see, so we can make a remark here. So if this is true, then that implies that there is no rational p equal to the square root of 2 is not rational. And if I remember my history correctly, there was a devotee of Pythagoras who lost his life over this fact. Maybe not square root of 2, but the fact that there's not that not every number can be written as a rational number. So remember, a rational number is so that is a number p that's equal to, say, m over n, where m and n are integers and n is non-zero. So this is a very interesting fact. And let's try to prove it. So how are we going to approach this? Well, let's suppose, so the claim is that there's no rational p such that this is true. So a standard approach to this kind of problem would be to suppose there is one and then try to obtain a contradiction. So that's called a proof by contradiction. Because if we could find a rational p that equaled that would prove the claim false. And on the other hand, if for any so let's see. So if we suppose that p is rational and p squared equals 2, if this always results in a contradiction, then if for any rational number p this cannot happen, that means that there is no such rational p. So we're going to try to obtain a contradiction. So that's our goal, is a contradiction. So we are supposing p is rational. That implies the definition of a rational number is a number that can be written as m over n. So it's a ratio where m is a integer, which we write as z, n is an integer, and n is non-zero. So the integers z here is the set of all the integers. You know all the integers, right? So it's -2, -1, 0, 1, 2, etc. All the integers. This is the set of all the integers. And this notation here just means that m is a member of this set. So m is one of these numbers. Maybe -47, something like that. So that this supposition implies this. And so let's suppose this, and suppose that p squared equals 2. So that means, p squared equals 2 implies m squared over n squared equals 2. And let's see, if we move the n squared over, we get 2n squared. So let's stare at this for a bit and see if we can see how to get a contradiction. So something about squares. and 2 here. Something about the 2 maybe? Maybe there's, let's see. Well, let's see. Alright, I'm stuck. M squared, so M squared, so M is some integer. M squared, you could visualize it as a square. N squared would be 2 times n squared is m squared. So n squared, 2 times that is m squared. But supposedly this does not hold for integers m and n. Oh, well, let's see. Maybe there's another approach. Suppose, maybe we could take, rather than just supposing p is any rational, let's choose a particular rational. So if there is a rational, then there's at least one. So we can choose one that has a particular property. So what property might be useful here? Let's see. Maybe, oh, okay, so another thing we can do, so we can choose this, so for any rational, we wrote it as m over n, but we could also assume here that m and n are co-prime, meaning that and we can also assume m is strictly positive, because if we can take care of the negative sign. If it's negative, we can make n negative, and so we can make m, well, at least greater or equal to 0. So coprime means that they have no common factor. So that means that if we write out the prime factorization of m and n, then they share no common factor. Because if they shared a factor, then we could cancel it in here in the ratio. So can we use this? I'm starting to see it. Okay, so let's write out. Haven't worked with, so I'm not a number theorist, so I haven't worked with this for a while. Let's write out the prime factorization of m. So we've got some primes, p1 through pk, and n we can write out as, let's say, q1 times q2 up through ql. And now let's see what this looks like. So that means p1 squared up to pk squared equals 2. Maybe this will help. So is this a problem? Now, by our assumption of coprimeness, none of these p's is equal to any of these q's. Let's see. Now, let's see. If this is equal... Oh, wait. If it's coprime, none of the p's is equal to the q's. But, okay, right. So a number has a unique factorization into prime numbers. So these here, all these pi's and qi's are prime numbers. And by the unique factorization of integers, every integer has a unique factorization into primes. And so this is an integer, and this is an integer. So the factorizations must be unique. But by our assumption that pi is not equal to qj for any I and j. So what does that tell us here? That tells us something important. And there's the 2, which is something which is kind of a bit strange. So staring at this, let's see, what does that tell us? I had to reset my timer there. Okay, so let's see, what does this tell us? So we've got 2 times some primes, each of which occurs twice, and we've got some primes over here, each of which occurs twice. None of these is equal to any of these. But there must be a 2 over here somewhere. So let's say P1 is 2. Okay, so if P1 is 2, so one of these has to be 2. Let's say Pi is 2. Well, Pi occurs twice in this prime factorization. So that means that the other, so right, there's a Pi is squared in here somewhere. So the other factor in the prime factorization must be one of the q's, because by the unique factorization. So that would imply that qj equals 2 for some j, but that means pi equals qj for some I and j, and that's contradictory to our assumption that these were coprime. So that is a contradiction. Okay, we got it. Maybe in a roundabout way, but we got a proof at least. And that should prove, so we get our contradiction, and therefore there's no rational such that p squared equals 2.